This lecture is going to be on global circulation of air. And we're going to look at how the Earth transmits or transfers its equatorial warmth and the polar cold air. They're going to be working in these cycles, or these convection cells that we'll look at. So we're really redistributing equatorial heat. This time not so much as by the ocean water, but by the atmosphere itself. So, and we'll look at how monsoons, which are large-scale land and sea breezes, are driven by PGF. So here goes. Once again, just to reiterate, we live in the zone, the mid-latitude zone called the Westerlies, that we are affected by our prevailing winds come from the west-southwest, and they kind of move in this general direction, to the east, to the northeast. So air moves in this general direction. So when we think of looking for, when we forecast what's going to happen with weather, we think of, well, look to the west to see what's coming our way. So a couple pieces that I want to make sure we make sense of. We're going to look at these convection cells here. This is the Hadley cell. This is an equatorial cell that acts between 0 and 30 degrees, and that's rough. That's kind of a rough estimate. But the underlying cause is the unequal surface heating. Very important here. The hot air is going to rise, that this is our equatorial low, where we find air rising, we get the adiabatic processes, and this is where we find our extreme, our large-scale tropical rainforest. So where we get tremendous amounts of equatorial storms and rain, we find the greenery within the tropical rainforest to support that. And so we have this 0 to 30 degrees is what was called the Hadley cell. So on the rotating Earth, there are 3 pairs of atmospheric cells that redistribute heat. So the Hadley cell is the 0 to 30 degree cell that's acting. This is once again convection. So where it rises here, it eventually subsides or falls back to Earth at about 30 degrees north and 30 degrees south. But we're going to emphasize, we're going to stay focused. We're going to spend most of our time and energies looking at the northern hemisphere. And 30 to 60 degrees, it's not labeled here, but this is the feral cell. So from 30 degrees here at the subtropical region, we have air, once again, we have air that's subsiding here. But we have a little bit more of a complex cell taking place here, because some of this Hadley cell continues to be transported towards the poles. But we do have this cell that's taking place right here, and we have the feral cell that's going to be influencing our westerlies, our local wind speeds and directions. So bear with me. And lastly, we have from 60 to 90 degrees, we have the polar cell. And if you'll notice that we have the polars are circulating, let's just say cold and less cold. Remember, temperature, warmth is driving these convection cells. So we're gonna be paying attention to the Hadley, the feral, and the polar cells. And this is an idealized global circulation. This is the equatorial low pressure, and air is going to be rising. And we're going to find that 30 degrees where we find this high pressure, remember, where air is sinking back towards the Earth, we're going to find some very distinctive characteristics. So here goes. So the subtropical high pressure zone, this is what we're looking at, 30 degrees, both north and south, but we'll focus on north. Air is subsiding, it is stable, and it's dry. It is near the 30 degree latitudes. This is the location of great or large-scale deserts. Air traveling equatorialward from the subtropical high produces the trade winds. Notice, here I have high pressure, equatorial low. This creates a pressure gradient force. It's going to be pushing air from the high to the low. It's going to be deflected to the right. So if I'm standing here facing the equator, it's deflected to the right. So my trade winds are this general direction. Out of the northeast, they're blowing to the southwest. Notice that the deflection is consistent with the Coriolis effect. The air traveling poleward from the subtropical high produces the westerlies, or the westerly winds. Notice subtropical high being moved towards the subpolar low. It moves high to low as your pressure gradient force. Deflected to the right, northern hemisphere is a component or an explanation of Coriolis effect. So find the subtropical high. This is your high that's going to be pushing air. And we get the westerlies, and this is responsible for why the air flows the way it does locally. So deserts reflect conditions of high pressure zones. So if I look at this here, I have the equator drawn in red, and I have Tropic of Cancer and Tropic of Capricorn. You'll notice that 30 degrees north and south, we find our large-scale deserts. And it's really a reflection of what we find with our equatorial low, our this particular low up here, it's going to be divided by, so I have a low here and a low here, it's going to be divided by the subtropical high. So we're labeling this. So I want you to go ahead and make sure you have this in your notes. We have low, high, low, and we have high pressure located at either end of the poles. So there's a pattern we see. Low, high, low, high. And therefore we can find deserts. Where we find high pressure, we find deserts. We find deserts at the poles as well. But the deserts we think of are the subtropical deserts. So high pressure is the result of descending air. Air falling towards the earth heats due to compression. This heat drives the relative humidity down, leading to warm, dry air. Where high pressure is found, at roughly 30-degree latitudes, both north and south, the landscape reflects the warm, arid air. So this is where we find the large-scale deserts. So here we can look here at the subpolar low zone. That's the region up here, roughly 60 degrees north and south, but we'll work with the north. We have warm and cool winds that interact. This is where we have polar fronts. This is the area in which storms are kind of born out of. So the subpolar low, 60 degrees north. And then we have the polar high pressure zone. Cold air is subsiding, and that's what we have right here. Air is descending. Air spreads equatorialward and produces the polar easterly wind. So if I have high here, I have low here, it's going to be pushed from high to low as my pressure gradient force. We see it deflected to the right, consistent with Coriolis. And the polar easterlies collide with the westerlies along the polar front. So this is where we find all kinds of weather makers, and these will be influencing us, and we'll talk about them as we move into this unit a little bit more. So the influence of the continents. So we get seasonal temperature differences that disrupt the global pressure patterns and the global wind patterns. So continents, lands, remember land and water heat up a little differently, or noticeably differently. So they're going to be interrupting. So it's not a perfect system. It's a very complex system, but we can make sense of it. And the influence is most obvious in the northern hemisphere, right? We have land. We have much more land northern hemisphere than the southern hemisphere. So we can look at monsoons. That a monsoon is the seasonal change of wind direction, and this is going to be influencing tremendous amounts of precipitation that are called monsoons. These are severe storms. So in January, we're going to find that the intertropical convergence zone is located at this location. This is an area of low pressure. However, when we compare that to the ITCZ in July, notice if I consider this, and I'm going to kind of work these back and forth just so you can see how it moves, it's following the pattern of insolation. That in January, it's located a little bit further south. And in July, it's located a little further north. I want you to pay attention to the winds, and we're going to follow, we'll just follow India and kind of the Southeast Asia for the most part. I want you to notice that during July, this is a large-scale sea breeze. However, in January, this is a large-scale land breeze. Well, land breeze isn't going to have the moisture. It's going to be much drier air because it's going to be coming off of the land. So when we look at what a monsoon is, it's actually driven by, it's creating these large-scale land and sea breezes, large scale. So when you get this warm, moist air that's moving onto land, you're going to get tremendous amounts of rainfall. So if I follow, once again, the intertropical convergence zone, in July it's located a little further north over a lot more land. This creates a large-scale sea breeze, whereas in January it's located further south, consistent with insolation patterns. The ITCZ is generating a large-scale land breeze. So you're not getting the monsoons in January, you're getting the monsoons in July. And that's what we're looking at. We're looking at these arrows here. Large-scale sea breezes. So monsoons. These occur over continents. During warm months, air flows onto land. Warm, moist air from the ocean. This is what's delivering the ingredients for severe weather and strong storms. You know, we're talking about rainfall measured at times in feet of liquid water. Tremendous amounts of flooding. But in the winter months, the air flows off the land, and it's dry continental. So we're comparing the difference between the January and July months. So just to kind of bring this back and close to finishing up here, I want you to see here global wind belts. When we focus on the Hadley cell, this is one of the primary drivers from 0 to 30 degrees. And then the Ferrel cell is from 30 to 60. These are the two primary convection cells that we are interested in for the most part. that we have deserts form, and when we look at the equator here in red, that 30 degrees north-south, there's a reason why we look at subsiding air, that this compression element that descends at 30 degree latitudes is due to Hadley convection cell. That we have Hadley providing descending air from the south, we have the Ferrel cell providing colder air from the north. So at 30 degrees is a very active zone of air that is compressing, heating, and drying out the land, anything it comes in contact with. It's so warm, so dry, it just sucks out any type of moisture. So we can see how high and low pressure, they work in tandem, circulating equatorial warmth with polar cold. And so to end this, the last one is I want to focus back onto the Westerlies for a second. The zone of the Westerlies, it's very complex. Airflow is interrupted by cyclones, and this is how we can start applying this. That cells move from west to east in the northern hemisphere. They create anticyclonic and cyclonic flows, and paths of the cyclones and anticyclones are associated with upper level airflow. And this is where it comes into play with the geostropic winds. Remember, the geostropic wind is pressure gradient force deflected by the Coriolis, so the net wind effect is going to be, we're going to label this, we'll see it in purple, that the airflow we're going to be seeing is this general this general pattern. Notice it gets deflected to the right because the further it travels, the Coriolis effect acts on it more. So geostrophic winds are, we're comparing upper level here, where you only have pressure gradient force and Coriolis affecting it, and we're looking at surface winds where we cannot ignore the fact that friction is acting on it in the opposite direction it's traveling. So really the light purple is the resultant wind vector that we notice. So our winds in the Westerlies, they're very complex. We have air masses that are coming from the Gulf at times. We have air masses coming from the Pacific at times, and we have dry air masses coming out of Canada. And where they interact, we get our weather that is, let's just say, comes in a wide variety, shapes, and sizes.